All right, so I will be kicking off the afternoon session, and my name is Kristen Beck. I'm a researcher at IBM Research, which is a really fun place because we get to do a lot of crazy things. It's actually where Watson started, which is what many of you know IBM for. And today I'm going to talk to you a little bit about food safety. So my talk timing is perfect because you've all just eaten. So if you're a Twitter-inclined person, my handle is up there, and feel free to tweet. So my talk title is Bringing Microscopic Data to Life Using R Markdown and Plotly. And I'm going to show you a little bit about the work that we do from a scientific perspective and how data visualization has made that better. Okay, so here's a little bit of a roadmap of what I'll be talking with you about. So you make pretty plots, but why? So salmonella is no joke. Has anybody here ever had foodborne illness, food poisoning? Oh, I got a woo on that one. Somebody liked it? That's weird. Okay. It's terrible. You feel miserable. You think you're going to die, and you wish you might. Hopefully you didn't. Otherwise, you wouldn't be here. But I work on food safety, and I'm going to talk to you a little bit more about some of the work that we do. So. We also are building out a platform called Macaw, which is the Metagenomics Computational Analysis Workbench. If this would have been before trivia, that would have been one of the questions. And I'm also going to talk to you about the data visualizations that we do to bring that data type to life, and some of the scientific objectives that are necessary to, or that generate the need for those kind of visualizations. So first things, food safety is stuck in the past. As many of you who have had a foodborne illness know, it's common, it happens. You may have had it more than once in your life. You hear things in the news all the time about, Chipotle, Bluebell, all of these different things, and a lot of people get sick. And in emerging countries where the healthcare system is not as robust as we are fortunate to have here, that can mean death for a lot of people. And so foodborne illness is a really big deal. And a lot of the testing that we use today in the US and other countries has been technology generated in the 80s that is just not where it could be to help people. A lot of the times with food safety tests, you're looking at single molecule assays that are binary in nature. Is salmonella there or is it not? And on top of that, they will require that food ingredient to be cultured in a lab where it's in an artificial environment and not actually natively representing the food ingredient anymore. So the tests themselves can be biased too. And so that's kind of what we're doing today, and that's the standard of protocol. So what IBM has started is the Consortium for Sequencing the Food Supply Chain. And this is a partnership between IBM, Mars, UC Davis, and Bio-Rad, where each partner brings a different interest area. Mars as in the maker of M&Ms and Uncle Ben's rice and Purina. And so the idea here is to use sequencing data for the microbiome to understand foodborne illness at a variety of different areas in the food supply chain. And in addition to foodborne illness, to also be able to detect and better understand things like food fraud too. And the idea with this is that just as we all respond to our environment, say around Christmas time, we all start getting a little giddy, we pack on a couple pounds, we respond to the environment. The microbes, the bacteria that live on food, will also respond as well. So if things on the food change, those microbes will change too. And so the idea here is to track those differences to better get a handle on when foodborne illnesses or outbreaks can become an issue. Okay, so it involves a lot of sequencing data. So for this project, we're generating hundreds of terabytes of raw sequencing data that looks like the A's, C's, T's, and G's that you guys heard about yesterday. And for any given sample, we have about 350 to 550 million character strings, about 150 base pairs or so that we need to distill into informative data. Is salmonella there? Is listeria there? Some of these kind of things. Okay. There we go. So you may still be asking yourself, what's a microbiome? So just a quick definition's sake, a microbiome is the sum of all microorganisms, bacteria, viruses that live in an environment, and not all bugs are bad. And so I'll be talking about the microbiome of food ingredients for the remaining part of this talk, and so this is kind of a way for you to catch up right now in case you're still confused. So some of the objectives that we have are to identify shifts in the baseline. Can we determine when those microbes are are different in response to a change in the food ingredient. And I'll take a side note here for a second. So this is my first time ever making an R-Pres. If others are interested, it's actually really fun. I forced myself to learn how to do this for this conference. And this plot here is shown on the left. It's behind me, so I have to make sure I'm reading it right. It should be. But on the left-hand side is something that I was like, oh, I know I wanted a baseline with a spike, and I could just generate the data as I needed, plot it, and in like 3 lines of code, I had the exact figure that I needed. So if you haven't played around with R-Pres, it's a great tool to use, and you write your slides in Markdown, you can embed Plotly graphs, so on and so forth. Back to the science. So the other objective that we're trying to understand is food fraud. So how funky is your chicken? If a food company sells you a truck full of chicken, is it actually chicken, or are you looking at something else? And today in the food industry, there's no single molecular test to identify if a food ingredient is the product that they say it is. It's not widely used, and what food companies are stuck doing is relying on the reputation of the renderers and the vendors that they work with. And you can get a lot from a reputation, but it's still not as bulletproof as, is this actually chicken at a molecular level? So one of the things that we're using this sequencing data is to understand and get at that question to better identify for food authentication issues. Okay, so for the project that we're working with, understanding all of these different food microbiomes, there creates a laundry list of data visualization challenges. For our group, we're working on a research focus. So the data should be precise, unbiased, and also allow for exploration all at the same time. So there's a lot of different uses that must be addressed for any given visualization. We also must address varying scientific questions. The questions that I ask might be different from a question that my colleague might be asking, and we want to be able to allow those kind of explorations through the data viz. We're also working with a high volume of data points, between hundreds of thousands to millions of data points for any given result. And sometimes that forced summary could inadvertently bias a user, so we try to be really aware of that as we go into the data visualization. In addition to that, we're working with really long categorical data terms, things like polyamine biosynthesis superpathway that might mean something to maybe one other person in this room. But if you were to try to put this up as a legend or labels on a plot, I mean, it just overwhelms the visualization. And this specifically is one of the reasons why I started using Plotly in general, because we would have a list, and this is actually shorter from one of our descriptive terms, that if you try to put in the margins of a PDF or PNG, you just swamp the plot, and it makes it really miserable. So having an interactive data visualization allows you to have the information necessary in those labels without disrupting the visual use. And in addition to this, a lot of our data visualization must tie in with existing bioinformatics tools. And people describe bioinformatics sometimes as the Wild West because it's a new field in scientific relative terms, and there's a lot of things that are created by graduate students that are no longer maintained after they graduate, and each of them have different data formats, and they're not really maintained, they're often not documented, so you're dealing with a messy type of data frequently. Sometimes it's nice. Sometimes it's clean, table data, but not always. So I'll tell you a little bit about how we actually bring these visualizations to our users. So we've built a web application called Macaw, which is the metagenomics computational analysis workbench, as I mentioned, where you can run all of these different bioinformatics tasks using a variety of publicly available tools or tools that we've created that will then provide a result. And that result then needs to be visualized. And so I built the Beaker package, -1E from the talk yesterday, same noun project icon plus a beak, that pulls in R and Plotly to visualize Macaw, data that comes out of Macaw. And so I'll show you a little bit about what that looks like now. So this is a screenshot of our web application. And on the left-hand side, is my mouse there? Yeah, okay. So on the left-hand side, this is our launch workflows panel, where a user could, for example, generate a list of bacteria in a sample, an organism, all those organisms, and they want to visualize that organism table. And so they select their input, and then they can select a variety of different parameters. Do they want to log transform the data? Is there an offset necessary for that? Do they want to get rid of things with zero variance? And for every single one of our people on our team to create or recreate this same kind of visualization, it would be a bit of a mess. So this ties in directly with the visualization engine in Beaker, where the parameters that are used can get passed into the R code, and then also be returned back using R Markdown to the user as well. Okay. And so the UI connection, so I kind of jumped ahead a little bit. So the UI connection between Macaw and R Markdown is that the parameters provided in this launch workflows panel end up making it through to an analytics panel. So the researchers can run their analysis inline and generate the reports at a single point, where they're not chasing around PDFs or PNGs that they sent around via email 6 months ago. It's all inline. In addition to this, we have an entire derivation chain for any action. So every single step that's been created to result in a visualization can be pulled as well, which really helps with the reproducibility. So I'll explain a little bit about what I'm about to demo, and then I'll show you what that looks like. So who you are is one thing, but how you behave is what really matters. And this is important for these microorganisms because you can apply a name to these microbes, but what you really want to understand is, are they actually producing these toxin genes? Are they making things that are going to make people sick? And so the analysis that I'll share with you next is what we call functional analysis, where you can see the functions that these microbes are doing. Make sure, okay, don't look. All right, so this is an example of our analytics tab. And you can see it, okay. Where inline you have the report that's a pathway report. And so the first tab that I've opened up to here is a descriptive tab indicating what the two variables that will be plotted in the subsequent plots are, pathway abundance and pathway coverage. These have a very specific definition, and if that is not explained, the user may not interpret the plots with their best judgment. So by providing this definition to the user, we increase their usability and their interpretation of the visualization. We can also provide information for people who may not be used to looking at Plotly graphs, like you can hover over things and you can zoom in, some of those really great features that a lot of people have spent a lot of time working on. You can provide summary tables. So this is a table of the median abundance value, which was indicated at the parameter that was provided by the user, to where you could either provide a ranked table or a median abundance value, and this information is passed through to the user through the visualization. And many of you may be in the experience of, you send off a PDF and 6 months later you have to try to remember how this was actually created. But by using R Markdown, you're able to encode that information directly at the point of information. Encode the helper information. And then we have a variety of different plots. And in this report, I've started off by kind of high-level understanding of okay, what are these different samples doing? How many of these samples have pathways that are present, shown here in the salmon color, and how many of these are absent? And you can walk through some of these figures to get an information of the data. You can look at shifts, for example, to say, okay, this sample has an abundance that's shifted to the right. It has a higher abundance than any of the other given samples. And without a visualization of this nature, you wouldn't be able to get that information. You can provide alternative visualizations in case people don't understand density plots. You can also throw a box and whisker plot, pathway coverage, and then if you wanted to look at some of the actual pathways present, you can again, and this is where I'm talking about the really long labels here, the super pathway of serine and glycine. And you can drill into this pathway coverage, abundance, and the pathway name at a single point, and even provide information that all of the hover values are 10 to the x, for example. This allows you to, this is the demo moment. Ah, it worked, okay. You can zoom in to where if you wanted to say, okay, well, what really is the highest point here? It happens to be aerobic respiration. So this is an indication of a growth pathway in this sample. And if we zoom out, this sample, and as a whole, the abundance is considerably higher than all the other samples. And the pathways that are most abundant are things involved in growing organisms. So you have bacteria that are growing. This is a sign that something could be wrong with this sample. Thank you. So that's a bit of a demo about some of the R Markdown that we're using, and I'll share with you a couple other visualizations that have helped us gain information about our samples too. So one of the other pieces that we've put together is a heat map using the Heat Maply package. And you see at this top region, this top right-hand corner, a lot of these microorganisms are black. And what this plot actually is, each row in here is the Latin name for, or at the genus level of a food matrix ingredient. So for example, here I've hovered over Bos, which is for Bos taurus, or cow. And you can see on the majority of samples that is non-existent, except for just a couple. And you can see that the predominant organism in these samples is chicken, which is good because these should be chicken samples. But many of you might have picked out already the one point indicating that something is different. And this is an ingredient that wasn't expected in the sample and couldn't be tested for any other molecular metric. Does anyone know what SUS stands for? Pork? Yes, pork, exactly. So we, the company here purchased a truck full of chicken, but they got a little bit of pork in there as well. And that can be a really big deal for people who didn't want to eat pork on purpose. So being able to visualize our data in this manner allowed this to be called out strongly through clustering with the dendrogram, and then also by the color gradation that this is one of the very high abundant organisms in this sample 4 that was not present or not present at that volume in other samples. Okay. One of the other things to understand the baseline differences, so this is getting back to bacteria now, so we've done the food fraud, now we're looking at the bacteria, is again looking at what microorganisms are present and how similar does that look. You will have bacteria in your food, you have bacteria on you, you have bacteria everywhere. There is a level of normalcy that will exist, right? If you look at the samples here towards the right, these look pretty similar in banding structure with slight fluctuations. But if you look at sample 13 to the left, you see that there are huge differences, and one of which specifically is a high signal of Klebsiella. And this is something that will make you sick, and that is a food safety organism of interest that is strongly called out by having this type of a visualization. This sample to the left was not a food ingredient sample. Don't worry, it's not made its way to the market. This was an on-purpose spiked sample where we were testing, okay, how do the microbes respond? Are they actually shifting the microbiome? Okay. So I would like to wrap that up to say data visualization is awesome. It helps food safety. If you're interested in coming to work with us, you can email me or you can direct message me. We're hiring interns for this project specifically from all the work that I've shown. And my colleague is also hiring a postdoc right now for image analytics. He just got a $25 million grant for the Center for Cellular Construction, and he needs some people who really know image analytics. So reach out to me. I'd be happy to talk with you, and thank you for your time. Are there any questions? Yeah.
So can you bring in workflows and add in the data to then do this, or do you have to use the, I don't know, like mother or chyme to analyze, or bin the sequences or whatever?
Right. So, do you mean for the Viz organism workflow specifically, or do you mean in general for Macaw?
Or I guess for Macaw.
Macaw, yeah. So Macaw is like a really agnostic platform where you can bring in a variety of different bioinformatics tools, and we do actually run chyme. So you can bring in publicly available ones for bioinformatics specifically. You could also bring in just general text analytics if you were interested in that. Yeah, so we can also put in custom analysis. It supports a variety of different languages, packages, executive, anything like that. Yeah.
Hey.
Hi.
Really nice presentation.
Thank you.
I'm curious because my field is different than yours, but it seems like your techniques are just pretty useful for signature detection in general. Maybe one might say latent categorical analysis or something. Mm-hmm. Is there a way that I can use your tools? Are they packaged in a package so I can apply it to something else?
That's a great question. So the visualizations I'd be happy to share with you. The Macaw platform itself is something that we use in-house. If you're interested, we can talk more, but it's not something that's open source right now because it's for the consortium, and so there's specific rules around what's public and what's not. But I'd be happy to share visualization code with you, or anyone really. So, yeah.
Excellent talk.
Thank you.
From my unique perspective, I was able to see about a third of the audience rethink their chicken parmesans. What kind of computational resources do you leverage for running the Macaw platform?
Yeah. So right now we have in-house 35 compute nodes that each have about 200 gigs of memory or so, and we're storing about 500 terabytes of data with capability for expansion. That's what you were asking?
Yeah.
Okay. 5 minutes. Any other questions? Okay. Thank you.